In this video, we'll cover the problem network delay time. In this problem, we're given three inputs. The first input represents a graph like this, a weighted graph, and it's directed as well. So we can see that from the 2 node, we can get to the 1 node, and it takes 1 unit of time. Then the other input is the number of nodes in our graph, and then the last input is some starting node. So here, k, our starting node, is 2. And we want to figure out the minimum time to send a signal from the start node to every other node. So here we can send the signal from 2 to 1 in 1 time, but to get to 4 it takes 2 units of time, so the answer would be 2. And they don't have other examples for us, so that is okay. Also, if it's not possible to reach every node, we return -1. Now, the optimal solution to this algorithm, or to this problem, uses Dijkstra's algorithm, but in almost all cases, that's outside the scope of a coding interview. So we are going to focus on how to do this using a depth-first search in today's video. So the conceptual idea is that we're going to start by building a graph because our input is an array of edges like this. So this says that we can get from node 2 to node 1 using a total of 1 unit of time. And we want to transform that into an adjacency list representation, or kind of a modified adjacency list representation that works well for weights. And we'll see that in a moment. Once we have our graph, what we're going to do is we're going to start a DFS from this node. And every time we reach a node, we're going to track how much time we have, how much time has elapsed so far. So for example, when we get to the 1 node, we'd say, all right, 1 unit of time has elapsed. When we get to the 4 node, we'd say 2 units of time have elapsed. But keep in mind there can be multiple paths to 1 node. For example, there could be an edge from 2 to 4 that uses 1 unit of time. So then we would reach the 4 node once with 1 as our time elapsed, and another time with 2 as our time elapsed. And we need to pick the best of these answers. So what we will do is we will have an array that has the minimum time to reach each node. And that also kind of functions as a visited in a way, because what we can do is say, if the time we took to get to this node is worse than whatever we have already found as the minimum time to reach that node, we can just stop. We don't need to continue doing our DFS because we found a worse solution. So let's go ahead and see what this looks like in code. First thing we'll do is we'll switch our function to ES6 arrow function syntax. I'm also going to rename some parameters. Instead of n, we'll have num nodes. Instead of k, we'll have our start node. First step is to build our graph, and that's going to take in the edges. So we can come up here. We can write this function. We'll write it generically, so it just takes in some edges. And it's going to produce a graph, which we will use a JavaScript object to model. Obviously, we'll iterate over each of our edges to store them in our graph. We'll destructure out the 3 properties here. So we have our source node, our destination node, and our weight in our edge. And what we want to do is we want to say graph at source at dest equals weight. So here, we're actually getting, our graph is going to contain objects in the values. The reason is because it allows us to use this syntax, which is really nice. If you want to figure out the weight to get from source to dest, you just do graph at source at dest. And again, to enable the syntax, graph at source must be an object that allows us to kind of check for this key dest. So if graph at source is already an object, we're fine. But what if graph at source is nothing and it hasn't been created yet? Well, then we need to add it. So what we'll do is we'll check if the source is in the graph, like this. If the source is not in the graph, then we can say graph at source is going to equal an object, like this. And I believe that should be all of the code we need to write for our build graph function. Now we'll come here, and now I'm going to create our array that stores the minimum time to reach each node. So I'll write min time to reach is how I'm going to name this, and I'll show you why in a second. And I'll talk about what we're filling it with and how we're initializing it as well. The reason I'm naming it this way is because if we want to figure out the minimum time to reach the 3 node, then we do this. So it'll read like min time to reach 3, which I think reads really nicely and kind of looks like English. Or we have like min time to reach node is the minimum time to reach whatever is in node. Okay, we're using an array. You'll note that they're numbering their nodes starting from 1, not from 0. That's why I'm doing this +1 here, because if we had 5 nodes, then, and we just did a new array of num nodes, we get 0 through 4, and that would be a little awkward. So I want 0 through 5, so we can just discard the 0 index and use 1 through 5. And I'm filling with infinity because we're going to continuously do math.min, and we want this value to be overwritten. Okay, now we will have some function that's going to do most of our computational work for this problem. So I'll call it find min time to reach. We can kind of think of it as like a component. So when we call this on the 3 node, we're saying, hey, find the min time to reach all of these guys in your component. So I'll say nodes in component here. We'll pass in the graph. We'll pass in this array because it needs to update it. We'll pass in, I guess we can pass the start node first, then that array, and then we'll have the time so far, like time that has elapsed so far, which is 0. So we can pause now and write that function. Graph. I'll write this, since it's going to be recursive, we'll just call it node. We can keep min time to reach as the name, and then we'll have time elapsed so far. Now we'll have our 3 steps. We'll have our base cases. We'll have our process node, and we'll recurse on our neighbors. I'll start with recursing on our neighbors because that's easiest here. First, the node might not be in the graph. For example, 1 here has no outgoing edges, so 1 would just not be in the graph. So we should first check that there are actually neighbors for us to look at. So we'll do this check. And if the node is not in the graph, then we just return. We don't need to do anything. Otherwise, we can get our neighbors by doing graph at node. But remember that this problem is a little different. Because we have weights, graph at node is actually an object. And all of the keys of that object are our neighbors. So here we need to do object.keys of graph at node. Then we can iterate over each of our neighbors and simply recurse on the neighbor. So we'll do graph, we'll do neighbor, pass the same array in, and then the time is going to be a little different. So I'm going to come back and fill that in right now. It's going to be whatever the time was so far, plus the time to get from the current node to the neighbor. So we can do time to reach neighbor. And remember the way we defined our graph. If we want to figure out how to get from source to dest, we just do graph at source at dest. So we want to figure out the time from our current node, right here, to our neighbor node. So we can use this syntax to get the time to reach our neighbor. Then the time we can pass as the time elapsed for our neighbor is just going to be the time that elapsed to get to the current node, plus the time to get from the current node to the neighbor. Using a little bit of space. Okay. So that should cover our recurse on neighbor step. We don't actually need to return anything. The only job of this function is to update our min time to reach array. Now, the first thing we can say is if we found a worse way to get to the current node than something we found before, we should just stop. For example, if we started by finding that, okay, we can go, first of all, imagine there's an edge from 2 to 4 that has a weight of 1. Then say first we explored that edge, and then later we explored the edge going to 3 and then got to 4. Well, when we got to 4 with a time of 2, we should recognize, hey, we already got here with a time of 1. This is not worth pursuing. So that's the check we're going to do for our base case. We're going to say if the min time we've already found to reach the current node is less than or is equal to the time elapsed so far, we can just stop. No need to continue computing anything. And with that, our process node step becomes a lot simpler. Because if we get here, we know that the time elapsed so far is smaller than the min time to reach our node. So then we need to update the min time to reach our node to be the new time elapsed so far. Okay, now this is all that our function needs to do. Given some start node here, it's going to traverse the entire subset of the graph that we can access from this start node. It's going to get the min time to reach every single node. When we come back here, we need to actually find our answer, which is going to be the kind of maximum of all of these values, right? Whichever node takes the longest to reach, that is really the maximum time. Here, this node takes 2 units of time to reach, so 2 is our answer. So we could do something like min time to reach all nodes is going to be the max of everything in our array. And to get the max of an array in JavaScript, we can just spread the array like this. In the end, we can return this value here. There's one exception here, though, which is that it might be the case that one of these is infinity, meaning we could not even reach that node. So if that happens and the max is infinity, we should be returning -1 to signify that we cannot reach all nodes. So we'll store a constant for that. So cannot reach all nodes is going to be -1. And here we'll say if min time to reach all nodes is infinity, return -1. Now there's one last little detail that we have to manage here, which is here we decided to do a +1, which means we're actually only using index 1 through num nodes, and we're ignoring index 0. So index 0 is always going to be infinity. And when we do our max here, well, index 0 contains an infinity, so that the max is always going to be infinity, and we always return -1. So I'll make one update here, and I'll just say we can just set, or we could even do this up here, it doesn't really matter. I'm just going to set the value at index 0 to be -infinity, so that it becomes irrelevant when we do our max computation over here. Okay, that should be all of the code we need for this question. So let's go ahead and see if it works. Works in that case, and if we submit, looks like it works there as well. All right, well, that's all for this video, and thank you for watching.